Our objectives for today are that you'll be able to compare what the basic unit of an ionic compound looks like compared to what we already learned about basic units of molecular compounds, which, reminder, are covalently bonded. And then you'll be able to tell the difference between properties of ionic compounds and molecular compounds, and you'll be able to tell me what a polyatomic ion is. So we're going to learn about those today. All right, we'll launch right into it because they're kind of long. Sorry. An ionic compound is composed of positive and negative ions that are combined so that the number of positive and negative charges are equal. So you can't form a compound and you can't form an ionic compound and have charges left over. Okay? They have to balance each other out in order for it to form. Unlike molecular compounds, ionic compounds are not isolated neutral units. So if you remember, it's possible to have one molecule of water where you just have two hydrogens bonded to an oxygen. Okay? You wouldn't be able to see it with just your eyes, but it's possible to have just one molecule that's just two H's and one O. Sodium chloride, made of sodium and chlorine, is an ionic compound, and you will not find just one sodium atom bonded to just one chlorine atom. Instead, what you'll find is a network of sodium ions bonded to chlorine ions. So that's what I mean when I say it's not an isolated neutral unit. You're not going to find just one unit of sodium chloride. You're going to find a whole bunch of sodiums and chlorines all bonded to each other. And we're going to take a look at what that looks like as we continue through this. But I just want you to understand they're not going to be by themselves the same way that covalent compounds can be. Instead, they're three-dimensional networks of positive and negative ions that are mutually attracted to each other. As a result, ionic compounds are usually crystalline solids. So you're usually going to find that because they form these three-dimensional structures, they wind up looking like a crystal. It's not to say that covalent compounds can't be crystals, because we had a covalently bonded molecular compound, sugar, in our lab that was a crystal, but a lot of ionic compounds tend to come out being crystals. And not crystals as in the like crystal healing, but just like a three-dimensional crystal structure. You can see what an ionic compound is made of by looking at its formula unit. This is the simplest collection of atoms from which an ionic compound's formula can be written. So remember how with molecular compounds we had a molecular formula, like H2O, that shows you what was in it? A formula unit is similar, except that because it is because they don't form discrete units by themselves, it's showing you basically the proportion of ions present in a given sample of a compound. To help better describe what this means, let's look at an example, okay? The example, sodium chloride. So NaCl is the formula unit for sodium chloride. What it means is Na means one Na ion, and Cl means one chlorine ion. But it doesn't mean that that you are going to find just one chlorine and just one sodium bonded to each other. What it means is that the ratio of ions in a sodium chloride compound is 50-50. If you take a sample of sodium chloride, you'll find 50% sodium ions and 50% chlorine ions. Whereas for calcium fluoride, which is calcium and fluorine, the ratio would wind up being 1 calcium ion to 2 fluorine ions. So it would be like 33% calcium, 66% fluorine. So the difference here is that a molecular formula can tell you there will be 2 hydrogen ions and 1 oxygen, not hydrogen ions, hydrogen atoms and one oxygen atom in one molecule of water. A formula unit will tell you you're not going to find one individual compound of sodium and chlorine, but when you find sodium chloride, it'll be 50-50% sodium ions and chlorine ions. That's our difference that we're looking at here. It still tells you what's in it, it just tells you a ratio of the ions. Okay? And the ratio depends on the charge of the ions. So you'll notice that a sodium ion has a +1 charge and a chlorine ion has a -1 charge, whereas calcium forms a 2+ ion, meaning it tends to lose both of its valence electrons and get a +2 charge, okay? Which means that it's not going to form a compound with just one fluorine ion, because then there would still be a positive charge there. So instead, it's going to form a compound with 2 fluorine ions that each have a negative charge, and as a result, balance the positive charge of the calcium atom. While ionic compounds don't form discrete units, we can still use Lewis dot diagrams to show how individual atoms of a compound might interact with each other. So let's see what that looks like. We know that sodium chloride, we're not just going to have one sodium and one chlorine atom. But for the sake of helping us understand how this process works, let's pretend that that would happen. Let's pretend that we would have one little sodium atom with his one little valence electron joined together with a chlorine atom that we know has 7 valence electrons. Well, after they were attracted to each other, the chlorine atom, which is much more electronegative than the sodium atom, would actually take the electron from the sodium atom, and we would be left with a sodium ion that has no valence electrons around it in the outermost shell, and then a chlorine atom that now has a full octet of electrons in its valence and has a negative charge to it. Yes, this is just in the outer shell. Sodium actually now has a full outer shell because it's dropped down to the shell below the one that was its outer shell before. So that's why this is stable for it. But we depict it without any electrons around it to avoid confusion. All right, what I'm going to have you do is I'm going to have you guys try this one. Okay, so this would look like a calcium atom, which we know has 2 lovely valence electrons. And it would need 2 fluorine atoms. So we would add to it our lovely friend fluorine, which we know has 7. Okay, and when you added them together, you would wind up with a calcium ion that was 2+, and 2 fluorine ions that now have their full octet and are at a -1 charge.
Does it matter if you do +2, +2+, or 1- or -?
I think the convention is the number first and then the charge, but I'm not going to dock you if you write +2 instead of 2 positive. All right. When atoms bond ionically, they find their lowest potential energy when they are arranged in a crystal lattice. Crystal lattice is basically an orderly arrangement of ions that is a 3D structure like a crystal. The attractive forces inside of this 3D structure are going to be oppositely charged ions. So in the case of sodium chloride, there would be attraction between all the different sodium ions and all the different chlorine ions inside this structure, as well as attractions between electrons and nuclei of adjacent ions. So just like in a covalent compound, there's still that attraction force between the nucleus of one atom and the electrons of a different atom. That force still exists. There's also repulsive forces inside of this 3D structure, okay? And that's charged ion. Man, I can't speak today. Like charged ions. So in the sodium chloride lattice, we would have the repulsion between two different chlorine atoms or two different sodium atoms, right? So they have like charges, so they're going to repel each other. And just like in a covalent bond, the electrons of different atoms are going to repel each other as well. So there's those repulsive forces. The distance between ions and their arrangement in the crystal represents the balance between these forces. So when we had a covalent bond, the bond length, how long that bond was, depended upon the balance between the attraction and the repulsion forces, right? The same is true inside of a lattice structure like this. It's just that you have to take into account that while a chlorine atom is being attracted to a sodium over here and a sodium up here and a sodium down here, it's also being repelled by chlorine atoms that are around it as well. So when we find a balance between those attraction and repulsion forces, that's why the atoms sit where they do in the crystal structure. Here are some images of a crystal structure to help sort of drive this point home and help it make sense. Okay? All right. In the image over here on the side, you can see that there's a sodium ion and then there's chlorine ions around it. What they've done over here in this image is they've taken the same structure that's on the left and they've just expanded the distance between the individual ions so that you can see the actual structure. So notice here on the corner, this sodium ion is attracted to this chlorine and this chlorine and this chlorine and this chlorine, and imaginary chlorine that's in front of it that we can't see, right? So we have to take into account all of those attraction forces, and it's also being repelled by this sodium and this sodium and this sodium and this sodium and this sodium back here. So all those different attraction and repulsion forces wind up causing this three-dimensional structure. And it's much more compact, like what's shown over here, but it's hard to see all the atoms in there, so they expanded it for you. We can also look on the next page at a close-up view of one individual atom. So you have a chlorine ion in the center here, and then there's, whoops, I forgot I wasn't drawing anymore. There are 6 sodium atoms that are all the way around it, right? And then the same is true over here. You just can't really see the sodium ion hiding in the center of all of these chlorine ions, but there are, again, 6 chlorine ions surrounding it. And when you group together a bunch of different groups like this and groups like this, you get the lattice structure that we saw on the previous page. Okay. As you can see in the images, each sodium ion is surrounded by 6 chloride ions, and each chloride ion is surrounded by 6 sodium ions, and the result of this is that the attractive forces of the oppositely charged atoms are stronger than the repulsive forces because the like-charged atoms are then placed much farther away from each other than the oppositely charged atoms. So it allows those attractive forces to be greater and produces a very stable and very solid structure, but it doesn't allow a lot of room for flexibility. So these tend to be very rigid compounds. The types of atoms involved, as well as the ratio of atoms in an ionic compound, determines the structure of the lattice. So remember that the length of a bond depended on which atoms were bonded in a covalent compound, right? If you had a hydrogen and a hydrogen bonding, the bond length would be different than a hydrogen and an oxygen. The same is true inside an ionic compound. And then on top of that, you throw in the fact that some ions, like calcium, require 2 ions to be bonded to them. So that change in ratio would also change the arrangement of atoms. So it's not always going to be, 6 around 6 like it is in sodium chloride. That only works because it's sodium and chlorine. If it was calcium and fluorine, it would need to be arranged differently. And the distance between the atoms would also be different because of the attraction forces being different, because different atoms have different electronegativities. Okay? So all that to say, just like different covalent compounds have different bond lengths, different ionic compounds have different lattice structures. And because of their complex lattice shape, comparing bond energies for ionic compounds is not as easy as just measuring the energy when a bond is broken. Instead, they measure lattice energy. Scientists measure lattice energy by measuring how much energy is released when 1 mole of an ionic crystal compound is formed from gaseous ions. So they take the ions that would form this compound and they put them in the gas form, and then they cause them to form into their crystal compound, and they measure how much energy is released for 1 mole of that. And that is what they say is the lattice energy of an ionic compound. So this is the equivalent of a bond energy for a covalent compound. And just like covalent compounds have different bond energies, different ionic compounds have different lattice energies. If you'd like to see some common lattice energies, they're listed in your textbook on page 189, figure 3.6. Just take note that those bond energies are listed as negative numbers because this energy is being released. Okay, now that we understand ionic bonds and how they form, let's talk about differences in ionic compounds and molecular compounds, specifically in their properties. Characteristics. Okay? Basically, the differences in the characteristics between these two comes down to the strength of the bonds at their base units. Okay? The attraction forces between the atoms in a formula unit of an ionic compound are significantly stronger than the attraction forces between atoms in a unit in a molecule of a molecular compound. That's because we're dealing with attractions due to charges as opposed to attractions between the nucleus of one atom and the electrons of another. It's just a much stronger force to be attraction between charged ions. As a result, we get different properties because several properties depend on the strength of attraction at base units, like boiling point, melting point, and hardness. Okay. Molecular compounds, which are bonded covalently, tend to have much lower melting and boiling points. Again, the attraction forces between them much lower, makes boiling and melting them require less energy. In fact, some of them require so little energy that they are gases at room temperature. Ionic compounds tend to have much higher melting and boiling points because of that stronger attraction. Ionic compounds also tend to be hard, much harder than molecular ones, but on the flip side of that, they also tend to be very brittle because of this. The reasons behind that are that in ionic compounds, you have that crystal lattice, right? And if you try to take a row of that lattice and shift it in any direction, you wind up putting like charged ions next to each other. And that increases the repulsive forces by a large amount. So, as a rule, it's difficult to do that. It's difficult to shift part of a lattice, which is why these are such rigid, hard crystals. However, if you do manage to have enough energy to do that, to move one of those layers, then that layer is going to just shear off. because of those repulsive forces, which is why they tend to be brittle and break as opposed to bend. The last property we're going to talk about is conducting electricity. So ionic compounds tend to be much better at this than covalent compounds. Solid ionic compounds themselves don't conduct electricity. So like you're not going to conduct electricity through just a pile of salt. But that's only because the ions inside the solid compounds are stuck. They can't move around each other, so they can't help move electricity through anything. If you were able to melt those compounds, so if you can get them to their melting point and make them molten, that would give them enough energy for the ions to move around each other, which would allow them to conduct electricity. A much easier way to do this, though, is to just dissolve them in water. When they get dissolved in water, because water is a polar molecule that has that partial positive and partial negative charge on it, it can exert attractive forces on the parts of this ionic compound and separate them from each other, essentially. And then once they've been separated, they are floating around inside the water and they can move around and help conduct electricity. So they tend to make excellent conductors of electricity when dissolved in water. There are some ionic compounds that will not dissolve in water. A lot of them will, but some of them won't, and that's because the base units have such strong attractions between them that even the polarity of water can't pull them apart. So they remain together and they don't dissolve. All right, the last thing we're going to talk about today is polyatomic ions. Polyatomic ions are what happens when a group of covalently bonded atoms gain a charge. They exhibit then characteristics of both molecular compounds, which are bonded covalently, and ionic compounds. Covalent compounds can form an ion if they have an excess of electrons. So if a covalently charged compound somehow bonded compound somehow acquires an extra electron, it'll gain a negative charge and become a negative ion. And if a covalently bonded compound somehow loses an electron, then it will become a positive ion. Whoops. Here are some common polyatomic ions. We have ammonium, which is a nitrogen atom bonded to 4 hydrogen atoms, and they lack 1 electron and therefore have a positive charge. And then nitrate ions, sulfate ions, and phosphate ions all have extra electrons, 1, 2, and 3 respectively, giving them -1, -2, and -3 charges. Notice that the covalently bonded molecule is inside the parentheses and then the charge is outside the parentheses, and that's to indicate that the charge is for the entire molecule and not just specifically one atom involved. Polyatomic ions can combine with other ions that have an opposite charge to then form ionic compounds. So then you would have a covalent compound inside of an ionic compound, because chemistry is fun. And we like to do weird things like that. You can draw the Lewis structure for a polyatomic ion using all of the same rules that we used to draw Lewis structures of our covalently bonded compounds. The only difference is when you get to the stage where you are counting up how many valence electrons should be in your compound, you need to add or subtract the number of electrons needed to give you your correct charge. Let me give an example. So if we were doing the Lewis structure of ammonium, which was that NH4+, we would do what we had normally done, and I'm going to give myself a blank paper for this, where we had nitrogen, which we know has 5 valence electrons, and then each of our 4 hydrogens, which each have 1. So if we're counting this up at this stage, we would say that it should have 9 valence electrons. Instead of doing that, we're going to say that it should have 8 because we know that our end product needs to have a positive 1 charge. So we're going to subtract an electron from our total. So instead of saying 9 valence electrons, we're going to instead say 8 valence electrons. So then when we go to build our structure, we can say bonds here. Okay, these guys have their octet. These guys all have theirs because they only need 2. And then we can count it up and 1, 2, 3, 4, 5, 6, 7, 8. So everybody has their octet, which is why we can't have that extra electron. Because normally we'd have NH3 and then nitrogen would have its lone pair up here, right? So if an extra hydrogen comes in, dragging its electron in tow, and it bonds to nitrogen, but nitrogen keeps its lone pair, then all of a sudden it has 9 electrons, which it does not want. So in order for this hydrogen to come in and join the party, one of these electrons has to go bye-bye. Okay? So you can still follow all those same steps. You just have to then subtract, or if you're going with a negative ion, you would add in extra electrons that you should have at the end. Sound good?
Can you
All right.
go back so I can get the drawing of it? I got the
Yes.
Oh, do